STEM chemist here, and I'm back with another great fun-filled experiment you can do at home. Today we are going to be working with soaps. So I have some dish detergent. Doesn't matter what kind, just any ordinary dish detergent that you got, and some dish detergent. Laundry detergent, dish detergent. Whoops. And some syrup, some corn syrup. If you have corn syrup. If you don't have corn syrup, no big deal. That's just to see if that's going to be added on once we get going. Oh, and some water. So laundry detergent, soap, and some, dish soap, and some corn syrup. You should have some corn syrup left over from last video. If you don't, it's all good. This is just going to help with some sticking later. Sticky solutions. So starting with soap. Soap is very, very useful. We all know what soap is used for, especially when we get real dirty, or when we're doing our dishes, or when we're doing our laundry with the laundry detergent. And there are other things that we have soaps for. For instance, if we're cleaning different types of stains off of a carpet, or if we're cleaning our cars, or if we're cleaning anything, any type of surfactant. That's another good word to Google. So we have some soaps. Soap. We're not going to start with the soap just yet. We're going to first talk about what soap is and how it starts off and where it comes from. Because it doesn't just start off as soap. It ain't like you just go outside and you see soap growing around. There's no way. So to create soap, there's laboratories and chemists and other engineers in industries to make soaps. Different types of soaps. For instance, this soap is different than this soap. And there's all types of other different soaps that we have. For instance, there's soap for our hair. There's soap for our body. There's soap for our carpet right over here. Soap for washing off the walls. Soap for mopping up the floors. All kinds of soap. Soap for washing our windows. Soap for washing our glasses. Soap for our teeth. We just call it toothpaste, but it's still soap. Soap. So soap starts off as triglycerides. Go ahead and Google that word, triglyceride. And what happens is that triglyceride goes through a process called hydrolysis. Another word to Google, hydrolysis. Hydrolysis means basically that triglyceride, which is a fatty acid or oil, it goes through the hydrolysis process with a strong base. And that strong base usually is like a sodium hydroxide, which sodium hydroxide also used for hair products. When people want to get their hair dyed or straightened or curled, whatever the case may be. But sodium hydroxide, also potassium hydroxide, is another strong base. And that hydrolysis process turns the triglyceride into a salt, fatty acid salt. Fatty acid salts, and the salt in that fatty acid salt, the salt in the fatty acid salt. Sounds cool. It could be like a song. Salt with the fatty acid salt. I digress. So the salt with the fatty acid salts, that is our soap. Soaps, and we have all different kinds of soaps, all different types of hydrolysis processes, all different types of triglycerides and fatty acids and fatty oils that we start off with to create different types of products that we need in the industry, whether it's for bathrooms, whether it's for cars, whether it's for body, whether it's for homes, whether it's for outside, cleaning off the carport or garage, or power blasting somebody's house, getting it nice and clean for the springtime and the summertime. But yeah, soap is used to clean things because it has a polar head and a non-polar tail. So that polar head is really cool as it has an attractability, so it attracts different things and it propels different things depending on its charge. So go ahead and Google that, what a soap molecule looks like. It's a COO with an R group. That R group spans with at least 12 carbon chains. So you have a carbon with hydrogens on the sides. But yeah, you'll see that when you Google the image. But yeah, soaps. let's get into some soaps. So soap, when we have soaps usually make what? Starts with a B. Bubbles. Soap always makes bubbles most of the time. And also there's bubbles right here coming from our water. So we'll go ahead and pour some water into your glasses. You don't have to fill them up all the way. We still got to make room for our, whoa, I missed. There we go. Also, make sure you have your 4 containers. I forgot that part. But you can see it here, obviously, in the water puddle. Ooh, that's pretty cool. So this right here is a pretty cool, I don't know if y'all can see that shot. Let me move this out the way. But the water right here beating up on the table. The surface tension is not breaking the water, so it's kind of just floating on top. But once that surface tension breaks underneath that water, like boom, like that, then now the surface tension underneath that puddle that was floating on top of the cloth here has broken, so now that water will slowly dissipate throughout the tablecloth. But other than that, it would have just kind of floated there. Like these right here, it'll still kind of be there, and it'll slowly disperse out, opposed to something that was agitated with me doing like my finger right here and sliding. Oh, y'all can't see that, that's why. But yeah, there's water right here, beat it up. I'll put it right here so y'all can see. See? I digress. Let's go back to some soaps. And straws. Make sure you have straws. And more straws. Oh, and balloons. Balloons. Speaking of balloons, that's what this next part is for. So go ahead and get a balloon and a straw. First, we're going to talk about some bubbles and how you can take your straw. We always know to use straws to get some liquid out of a container, but we also blow bubbles like this. And you can see the air that you're pushing through this tiny straw is going into the liquid. And the air has to go somewhere. So that air is a gas, and that gas bubble floats right back up to the top of the surface and pops. And you can see all these bubbles here are popping. And there's no more bubbles because what happens is all the air around us is weighing down on that water. And that water is sitting on top of water. And the bubbles is water. Well, the bubbles is gas. And the gas that I'm pushing down in here, that gas is being trapped around the water, and then that gas bubble floats back up and then pops, and then the water pops. The water drops back down, and it only drops back down because it's in a glass container, this solid. Because if it was not in a solid, it would just kind of fall out like this. If I was to say, for instance, put it in my hand, I can't hold water for nothing. Alright, so let's go ahead and take a balloon. And now, blow the balloon up. Add some air to it. Now there's gas that comes out if you let it go. So what we're going to do is trap that gas with our balloon as much as possible. With our straw, mind you. So now we have this. So you take it, pinch it, and just kind of pinch it along with the balloon, like so. And boom. And then if you have tape, you can tape it. But if you see, slowly let that pinch go, you can see, look. The gas that's in this balloon is making these bubbles, right? And you can see the popping of the bubbles at the top of the surface. See? Because the air around the top of the surface is heavy and weighing down. I'm gonna let that open up some more. Weighing down. And you can see the balloon is starting to decrease, but we still got bubbles. And if I let go a little bit even more, it gets very, very rumbly. But then it stops because the balloon is all gassed out. So we see here that the gases that we have in our body are very powerful, And if we are able to trap this gas in all different other fashions, then maybe we can transfer energy into some systems. So this is just an idea to think about how to take something as simple as blowing some air into a balloon, attaching it to a straw, and taking this potential energy and turning it into kinetic energy. For instance, similar things like this, steam engines, aqueducts, hydroelectric power, all types of fun engineering science. So let's go ahead and add some soap to pick a container. Any container, I don't know, this one speaks to me because this is the one I wanted to start with. So I'm going to take some and put it in here. There we go. So this is soap inside of water. You can see the soap is much heavier than that water unless I add more. We remember from that density last time. We're going to now add some more. And there we go. That soap is obviously heavier than the water. Mixing sticks are somewhere around here. Oh, there you go. Mixing sticks. Let's go ahead and mix that up. Mix it up. Or just swirl it. The good thing for an Erlenmeyer flask is what it's for. There we go. Got it mixed. And you can already see our bubbles starting to form. Now these bubbles on top are very different than our bubbles over here. Now that's because, remember, our soap is fatty acids and salts from fatty acids. So it has some elasticity in it, stretches and stuff. And it also traps dirt and all of that. But now what we want to do is the fun part. Take a straw and you'll see as you blow down in here, you can trap the gases with the soap. And now there's a lot of bubbles around her. But if you look closely, you'll notice that these bubbles are very symmetric, if you would. There are only 3 bubbles that can touch each other at once. If you were to force a 4th bubble to kind of come in contact and touch that bubble, one would pop, because the surface tension, the surface angle of a bubble, it's a good shot right there, is 120 degrees. So a full circle is 360. And then if you look carefully right here, there's only 3 bubbles touching. I don't know if y'all can see that. See that? Put it where my hair can kind of do some. But yeah, this is a pretty cool shot. Let me get closer so y'all can see the light. Let your light shine down. Ooh. So if you look carefully. Look carefully. Uh-oh. Whoop. Pop. Let's do that again. Alright. Here we go. Now this is a lot more bubbles to look at, but you can look carefully that there are no more than 3 bubbles touching at once. And you can see triangles beside the bubbles and around the bubbles, because that's 120 degrees, and that 120 degrees is the surface angle of a bubble. That's why only 3 bubbles touch at once. Bubbles. All right. Now, right here, this container has a much smaller lid, if you would, so they're forcing the bubbles to go through a very narrow space. That's why you get kind of this spillage, and it kind of funnels out. I'll do it forward so you can see. And it's going out in the shape of our container. But if we was to, for instance, let's take some dish detergent and put some laundry detergent in there, which looks totally different. And is it more viscous or less viscous than our dish soap? Remember what viscosity is. Is it more viscous or less viscous? You saw how fast it came out, right? This came out a little slower. So, more viscous or less viscous? Alright, so viscosity, remember, is thickness, how thick something is. So, viscous, how thick it is. Which one's more thick? This one is thicker. Alright, so, we have two different containers here. And you can see even, actually, look at that. The soap, look how thick that is and how heavy it's just kind of sitting down at the bottom. And when I poured that the laundry detergent in, it just mixed right on in. It is very, very more soluble than our, as you can see, our heavy soap here, which is our Dawn 4 times concentrated thick stuff. So we have to really, really give this some stir action. Stir it up. Now, let's see which one makes the more bubbles. This I probably put more of, but this is 4 times concentrated. This is, I think, 2. No, this is the single stuff. So this is just concentrated once. So this should have about equal soap. But remember, it's different soaps. So this, we're going to do some bubbles over here and bubbles over here and see which one makes the most and the biggest bubbles. And then this is for our syrup here in a second. All right, let's go. All right. Not bad. Set that over here. Let's do this one. Whoa. Now you can see obviously there are a lot more bubbles and there are a lot much more suds down here in the bottom right here. So this was really going to start to erupt. So this will tell you that the soap in our dish soap is a lot heavier concentrated, so there's more of it, so you don't have to use as much. In our laundry detergent, you can see it wasn't making enough suds as fast as this one is, as we just saw. Let's go ahead and do this next part. Make sure your hands are dry. Go ahead and get a towel, dry your hands, or find some cloth that's near. So if I was to try to take my hand and reach in here, I cannot touch a bubble for nothing because my hand, well, there's some suds on top, but I can't like grab a bubble. Why can't I grab a bubble? That's because of surface tension, and our hands are really rough compared to these bubbles. Opposed to if we feel them, or even if we got lotion on or oils, we feel our hands and we think, ooh, they're soft, nice soft hands. But these bubbles are very delicate. So to place that, to be able to touch a bubble, you must become the bubble. So, yeah, I mean that. So what you have to do, for instance, I'll keep this hand dry. Let's go ahead and get me some bubbles. Well, take one hand and get you some soap suds on it. Make sure it's nice and lathered, and you can feel the difference. So once you become the bubble, you can actually touch the bubbles. So let's go ahead and make some bubbles. All right, bubbles. So now this is my non-bubble hand, and I cannot grab it. Bubble hand. Look at that. I can grab bubbles all day with this hand because I am the bubble. And when you become the bubble, you are the bubble. So be the bubble. One with the bubble. So now this hand is a bubble too, and it can go in this one and grab these bubbles. Because we have made our hands a lot more smoother and equal to the surface tension of a bubble per se, opposed to the surface tension of our hand, which is nice and rough. But if I come down and put this on the table, which has a really, really, really rough surface tension, you can see all these bubbles start to pop, And that's why we get our hands with a towel and dry them off, or the couch, as I'm doing, or pillow. All right, let's make some more bubbles. Oh, that's done. The glycerin. So well, it's not glycerin. I didn't have any glycerin, but if you have glycerin, use glycerin. Glycerin works as well. Actually, better. Let's go ahead and add some syrup. Let's add some more syrup. Why not? Let's make this fun. Overindulge in science. It actually makes the best experiment sometimes. Unless you're doing microbiology or micro chemistry, then you want to use some stuff. But on this stuff, we want to make sure that you all can see it. So visibility is everything. So mix that up, mix that up. So what we're doing here is basically adding some elasticity to our soap. And this should help make bigger bubbles, larger bubbles, and bubbles that stick and last longer, of course, because we added in some syrup, some more fat. All right, here we go. Or sugar, rather. Here we go. Whew. All right, so you can see now, actually, the bubbles aren't popping as fast as they usually would. So by adding some syrup to it, it has made it a lot more elastic, and the bubbles aren't popping as much as they would. As you can see, look at it. Let me pull this on. It's kind of got a little bounce to it. See that? Usually if I was to do this with regular bubbles without the syrup, it would pop. Unless I squeeze it, of course. Squeezing it always gives pressure and force. Let's add this to this. So this is our stuff. Add some syrupy stuff to it. Okay. Pour some out. Okay. And here we go. Woo! This is getting big, y'all. Look how big this is. All right, let's see if I can go longer. Whoa. Whoa. I even got some on myself. Look at that. Bubbles. And you can see, look, it kind of looks like Africa. So this, you clearly can see adding the syrup allows the bubbles to stick together a little bit better. I got a bubble on my face. So you can clearly see the bubbles are sticking a lot better. And look at that. Got that bounce, bounce, bounce. Gotcha. Bounce, 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 Once you become the bubble, you be the bubble. Now, got a bubble fist. Bubble fist. All right, so we learned a lot about bubbles today. As you can see, these bubbles are going to be sticking around a little bit longer. I'll try to break them out this way. Thank you all. I appreciate you all taking the time out and having some bubble science with me today. Make sure that you are practicing safe science and have fun. And this video is going to make you clean for sure. Have some bubble fun. Well, this has too much liquid, so pour some out before you have your bubble fun. Let's see.